Okay, so in this video, I'm going to continue the discussion of the division algorithm, and we're going to use it in a much more complicated situation, and this is called the Euclidean algorithm. It's used for a lot of things, the simplest of which and the most immediate of which is finding the greatest common divisor, or the GCD. And here's how we do that. We use repeated iterations of the division algorithm. And each time I use the division algorithm to find a quotient and a remainder for a given A and B, then I use this BARB acronym to help me figure out how to set up the next step. And so what I do is every time I'm done with one step, then I use the B from the previous step, and that becomes my new A. And then I use the R from the previous step, and that becomes my new B. So B becomes A, R becomes B, it spells BARB. So that's how I remember how to set up my next step. And I keep this going until I get a remainder of 0, and I will always get a remainder of 0. That's something that's been proven. It's in your textbook if you want to look it up. And so the R that I get before I get 0, right before I get 0, that is going to be my GCD. All right, so let's try that with a couple of examples. The first example we have uses A as 375 and B as 165. So let's set it up where 375 equals some number times 165 plus a remainder. So if I figure out how many times 165 goes into 375, it goes in twice, and the remainder there is 45. Okay, and so now to move on to the next step, my B, which was 165, is now going to become my new A, and my R is going to become my new B. So now I'm going to see how many times 45 goes into 165. And if you check that with the calculator or mentally, it goes in 3 times with a remainder of 30. So now 45 will become my new A and 30 will become my new B. So now I'm looking to see how many times does 30 go into 45. Well, it goes in once with a remainder of 15. And then now I'm using 30 and 15 instead. So how many times does 15 go into 30? Well, it goes in twice with a remainder of 0. So now that I've got a remainder of 0, I look at the remainder that I got just before that, and that is 15. That means that 15 is the greatest common divisor of 375 and 165. Okay? So it's as simple as that. So let's do another one. If you want to pause during this example and just try it out on your own and check to see if you're right, you're welcome to do that. Or you can just follow along. I'm going to use 972 and 171. 171 goes into 972 5 times with a remainder of 117. So now I'm going to use 117 and 171. 117 goes into 171 just once with a remainder of 54. So now I'm going to repeat this process using 117 and 54. 54 goes into 117 twice with a remainder of 9. So now I'm going to repeat this process using 54 and 9. And 9 goes into 54 exactly 6 times with no remainder. So that means I'm done. And then the remainder that I got right before 0 was 9. So 9 is my GCD, my greatest common divisor of those two numbers. So the process is as simple as that. Now, something that is not as immediate but also helpful is you might want to find solutions to an equation where the two numbers A and B that you're given are the coefficients of x and y, and then the number on the right, the constant, is the GCD of those. So in the first example we did, we had A as 375 and B as 165, and we figured out that the GCD was 15. So how can I find a particular solution? And remember, it has to be an integer solution because we are only dealing with integers. How can I find an integer solution to the equation 375x plus 165y equals 15? Well, the way to do that is to do your steps of your Euclidean algorithm backwards. And we're going to set the remainder equal to a minus bq. So just to show you what that looks like, I'm going to start with the step that's second from the bottom because it has 15 in it. And I'm going to write it as 15 equals 45 minus 1 times 30. You can see that that's a simple arrangement of the second to last step. All right, so what I do when I'm done setting it up that way is I go up to the next or to the previous step where the remainder was 30, and I'm going to replace 30 with a minus b cubed from that step. So 165 minus 345. So everywhere there's a 30 here, I'm going to replace that with 165 minus 3 times 45. Okay, and it only showed up once, so that's the only time I've got to replace it. What I'm going to do now is I'm going to simplify these parentheses by distributing the negative 1 to the 165 and to the negative 3 times 45. So the 45 is fine, but when I distribute that negative 1, it becomes negative 1 times 165 and positive 3 times 45. And if I notice, I've got a 45 over here and I've got 3 times 45 over here. Well, I'm going to collect those and make it 4 times 45 and then leave the minus 1 times 165 the way it is. So now that things are simplified again, I'm going to go up to the remainder that I got before 30, which was 45. So everywhere there's a 45, I'm going to replace that with 375 minus 2 times 165. And so that gives me 4 times 375 minus 2 times 165 minus 1 times 165. I'm going to distribute the 4 just like I did before, and that's going to give me 4 times 375 minus 8 times 165, and then I've still got that minus 1 times 165 over here. Well, again, I've got terms that I can collect. I've got negative 8 times 165 and negative 1 times 165. And if I collect those, I get negative 9 times 165. So I was looking for a solution to the equation 375 times some integer plus 165 times another integer equals 15. Well, it looks like that's what I've got. I've got 375 times some integer plus 165 times another integer all equaling 15. So a particular solution to that is x equals 4 and y equals 9. All right, so that is just one of many solutions to this equation up here. So that's a more helpful application of the division algorithm. Let's do another one with the second example we did. Remember, we figured out that the GCD of 972 and 171 was 9. So I'm going to find a solution to 972x plus 171y equals 9. And if you remember, I'm going to start with the second to last step where 9 was the remainder, and I'm going to rearrange that so that 9 equals 117 minus 2 times 54. I go to the step above that where the remainder was 54, and I replace every 54 with 171 minus 1 times 117. Okay? And just like in the last example, I've got that negative 2 sitting out front, so it will be distributed to both terms inside the parentheses. So the 171 will become negative 2 times 171, and the negative 1 times 117 will become positive 2 times 117. And again, we've got some terms that can be collected. I've got 117 here, and I've got 2 of them over here. So I'm going to collect them and make 3 times 117 minus 2 times 171. Okay, and that's as simple as I can write that. So I go to the step above where the remainder was 117. And I replace every 117 with 972 minus 5 times 171. So this 117 is going to be replaced right here with some parentheses. So it's going to look like that. And again, that 3 outside the parentheses can be distributed to both terms on the inside. So I have 3 times 972 minus 15 times 171 minus 2 times 171. And just like in the last example, I'm going to collect the 171s. So I've got 9 equaling 3 times 972 minus 17 times 171. So that is a solution to this equation. I wanted 972 times an integer plus 171 times another integer to equal 9. And the x that I'm looking for would be 3, and the y that I would be looking for would be negative 17. So that would be my x and my y. I guess I didn't write them down, but that's what my x and y would be for that example. So we're going to do more of these in class, and just like before, if you have questions, let me know, and I will see you tomorrow.